In this video, we are going to work a little bit more with partial pressure and look at a slightly different way to attack our partial pressure problems. So if you remember the final problem in the previous video, we found the total number of moles, total pressure, and then we had to go back and find the individual partial pressures and did individual PV equals nRTs for those. Some of you may have been thinking there has to be a simpler way to do this because we know that the pressure is going to be proportional to the number of moles, because the more moles that we have in the system, the more molecules, more collisions with the walls of the container, therefore the higher pressure. So that brings us to the mole fraction, where we look at a ratio of the moles of the substance to the total number of moles. We use the Greek letter chi to represent that. So our mole fraction is equal to the moles of what we are looking for over the total number of moles. And that is also equal to the partial pressure over the total pressure. All right, so in this example, we are given the partial pressure of nitrogen as 592 torr and the total pressure of the air. We remember from earth science that nitrogen is the most abundant gas in our air, so it makes sense that it would take up a large portion of it. So anyways, we are looking for the mole fraction of nitrogen. So the way that we can do that is going to be equal to the pressure of nitrogen over the total pressure, because it's going to be proportional to the moles. So all we do is 592 divided by 752. And if we put that into our calculator, that gives me 0.787. There are no units on mole fraction because the units cancel, and it is expressed as a decimal, even though it says it's mole fraction. So 0.787, which would correlate to about 79%. All right, this is a continuation of the previous problem. So what is the partial pressure of the nitrogen if the same container, so we've got that same container from the previous problem, is compressed to a new pressure of 5.25 atmospheres? So what we can do is we can use our mole fraction would be equal to the pressure of the nitrogen over the total pressure. So since we have not opened the container and added or subtracted any gas, the mole fraction is going to stay the same as what it was in the previous container, because again, we haven't added or subtracted any gas. We have just compressed it to a higher pressure and a smaller volume. All right, our total pressure, our new total pressure is 5.25 atmospheres, and we are looking for the new pressure of the nitrogen. Once we do the math, that would be equal to 4.13 atm. So again, the reason why we could do that is because the moles are going to stay consistent. All right, another application of partial pressure that we are going to use very frequently is vapor pressure. So if we are collecting a gas over water, we have to account for the fact that even at a lower temperature, some water will evaporate. So some of the gas that is collected would be H2O, would be water vapor. So we need to take that into account in our problems. Now, often they will tell us the water vapor pressure within a problem. All right, so if we take a look at this, we have potassium chlorate decomposing, producing oxygen gas that's collected over water, as shown in a figure. So that's a figure from your textbook. So again, we'd have the oxygen gas being collected over water. So there would be an inverted jar of some sort that's collecting the oxygen gas, but you're going to have a little bit of water vapor in there too. So, in order to be accurate, we need to figure out how much water vapor is there so that we can figure out how much oxygen is truly there. So, they give us the volume, the temperature, total pressure, and the water vapor pressure. We are looking for the moles of oxygen gas and then through stoichiometry, figuring out how many grams of KClO3 were decomposed. So we are going to have to do a PV equals nRT calculation to calculate the moles of oxygen that are produced. Now, if we just put 765 in for this pressure, that is going to give us the moles of oxygen and the moles of water. So what we need to do is first figure out just the pressure of the oxygen. So that would be the total pressure minus the water vapor pressure. So we would do the 765 minus 25, and that would give us 740 torr. So that just subtracts the pressure from the water vapor. So therefore the moles of the water are not counted, and it will be just the oxygen that is being counted. So now we're going to take that, put that into PV equals nRT. Again, we are solving for the moles of the oxygen. Since we are using torr, we will use the 62.36 constant. And remember, the temperature does always have to be in Kelvin. So that would be 299 Kelvin. So once we put that all into our calculator, I get 0.00992 moles of oxygen gas that were produced from the reaction. Now, in order to figure out the grams of KClO3 that were decomposed, I'm going to need the reaction because I will need the stoichiometry. So KClO3 would decompose into KCl and oxygen gas. Now we would need to balance the equation, obviously. So that would be a 2, and a 3. So then through stoichiometry, all right, so then through stoichiometry, I'm going to take that 0.00992 moles of O2 and using the mole ratio from the balanced equation, so 3 moles of O2 will produce 2 moles of KClO3. And then I will use the gram formula mass of KClO3 to turn that into grams. And that is 122.55 for the gram formula mass. So then I put that all into my calculator. And that gives me 0.811 grams of KClO3. So in this problem, we used partial pressure, we used the ideal gas law, and we used stoichiometry.